Hello and welcome. Today, let us discuss about cyclic or ignorable coordinates. This is a very short topic that we will be discussing, but this is a very important topic. In first part of the lecture, we will define or we will say what cyclic or ignorable coordinate is. Along with example, we will illustrate with example, and in second part of the lecture we will talk about the relationship between cyclic coordinates and the physical nature of the motion of the system. For example, say conservation of linear momentum or cyclic or angular momentum or conservation of energy, and these conservation laws are in fact related to cyclic coordinates. So that relation we will see in the second part. Let's see what is a cyclic coordinate. So the question is, what is a cyclic coordinate? So if we look at the definition, it simply says that whenever the Lagrangian function does not contain a particular coordinate qk explicitly, then the generalized momentum corresponding to that particular coordinate pk is a constant of the motion, and that coordinate qk is generally known as the cyclic or ignorable coordinate. So let us see how whatever statement we made here is or can be seen from the knowledge that we already have about Lagrangian. Okay, so to begin with, so what we need is to recognize the fact that for a system, so let me just write down here. For a system described by a set of, say, generalized coordinates, let us just denote by q I, okay, and generalize velocities qi dot. We can write the momentum, generalized momentum pi to be del L by del Q I dot. So this we already know. So first thing is to recall this expression, and in this and by the way, this generalized momentum has other names as well. So this is also referred to as canonical momentum. So this is another name of the generalized momentum conjugate to this particular coordinate q I. Okay, so now if we just put this in the Lagrangian equation of motion, or in Lagrange's equation of motion, so that is d by dt dl by dqi dot minus dl by dqi equal to 0. Okay, so in this we'll just use this expression of pi here, instead of dl by dqi we put pi, that is this implies d by dt of pi equal to del L over del Qi. Okay, that is Pi dot is nothing but del L over del Qi. Okay, so this is the expression that we need in order to see whatever we stated above. So let us just put some equation number 1 and 2 for easy reference later on. Okay, now let us move on and say that in the so a particular Lagrangian, okay, a Lagrangian say L is expressed in terms of qi dot and t. Okay, this is the usual expression, and let's say I goes from say 1 2 3 and so on, say let's k, and say there are n number of generalized coordinates available for some particular system. Okay, we don't know, this is general discussion. In the example it will be clear. Now let's say this particular coordinate q, k, is absent, okay, in the expression of Lagrangian. That is so let us just write if qk is absent in the expression of Lagrangian. Okay, we're talking about the absence explicitly. Okay, so in this case we can write that say since Lagrangian L is no longer a function of qk, then we can write del L over del qk to be simply 0, right? So this implies from our equation 2 what we have is pk dot for this particular coordinate with subscript q is del L over del qk, which is 0 as we have just calculated here or shown here. So what does it mean? It simply means that your time derivative of the momentum for the particular coordinate denoted by subscript k is 0. That is our pk, which is the momentum corresponding to this generalized coordinate qk, is a constant. Okay, so this is what we have stated at the beginning. You see, whenever this coordinate qk or is absent in the expression of the Lagrangian explicitly, then we see that from by using the Lagrange's equation of motion here, immediately we find that the momentum for that particular coordinate or corresponding to that particular coordinate is a constant of the motion. Okay, that is pk is a constant of the motion. Okay, so this is the proof, or this is how we see the generalized coordinates. Okay, so we can also state as follows: the generalized momentum associated with an ignorable coordinate is a constant of the motion, is a constant of the motion. Okay, so motion for the system, obviously. So let me just stop here, but implies that we're talking about a system. So now let us see an example to see what we have just discussed. Okay, so for example, let us talk about, say, spherical pendulum. So spherical pendulum of mass, say m, and length, say l. Okay, so this is much like a simple pendulum, but okay, let me just draw it for you. So this is the vertical line. So we have a simple pendulum which is inclined at some angle theta from this vertical line. Okay, let's call this theta, and this bob is allowed to rotate about this vertical axis, and this angular change or angle defining the rotation about this plane is denoted by phi. Okay, this is the point where the pendulum is attached. The only force that is acting in the system is gravity, so let us denote it by acceleration due to gravity here. Now for this system we have to identify the generalized coordinates. So let's see what are the generalized coordinates for this system. Okay, generalized coordinates. Okay, there are two, one is theta and another being phi. Okay, so in order to write down the Lagrangian, as usual we have to calculate the kinetic energy and the potential energy. So kinetic energy, okay, is consisting of two parts. So let me just write half m l square theta dot square. Okay, l is the length of the pendulum. Okay, plus half m l sine theta whole square phi dot square. So as you can easily recognize, this would be corresponding to this theta, and this corresponds to this phi. You see, l sine theta is nothing but the perpendicular distance from the axis of rotation. Okay, this is l sine theta. So this is describing, the second part is describing the kinetic energy associated with the rotation about a plane where you define by this angular displacement phi. Okay, so that is all right. So this is our kinetic energy. Now what about potential energy? Okay, so for convenience or to make life easy, let us take the point where it attach this level to be potential 0. So whatever we measure, then the potential will write as negative. So potential energy U is negative mg, the height being the L cos theta. Okay, so this is the height. So we have the expression of kinetic energy and potential energy. Now our Lagrangian, okay, our Lagrangian L is T minus V. So the Lagrangian looks like L equal to half ml square theta dot square plus half ml square sine square theta phi dot square plus mgl cos theta. Okay, so from this expression we can see how the generalized, we will see the concept of generalized momentum. So let us just calculate let's see, let us check p k dot dl over del qk. Okay, so let's first check for theta. Okay, for theta, and here let me just write down the Lagrangian so that we don't have to flip it back again. Half ml square theta dot square plus half ml square plus mg cos theta. Okay, so for theta what we have is p theta dot is, you see, del L over del theta, which is straight away we can calculate here. You see, it gives us ml square sine theta cos theta phi dot square. Okay, now this is not 0, and we can also calculate p k, which is given by del L over del qk dot, and so this p theta is del L over del theta dot, which is, from here we can immediately see ml square theta dot. Okay, and similarly for phi we can calculate p phi dot, which is dl over dl phi, which is, as we can see in the expression of Lagrangian here, there is no appearance of phi, explicit appearance, so this gives us 0. Okay, and this implies p phi is constant. Okay, and we can look at how the p phi looks like. Okay, from this expression of p phi equal to del L over del phi dot, which will give us, you see, m L square sine square theta phi dot. You see, now we have the expression of p theta. Okay, let us just write pk. For theta it is ml square theta dot, and phi, which is ml square sine square theta phi dot. Okay, so this here is not a constant of the motion, but this here is a constant of the motion. Okay, now you see, this constant of the motion is also referred to as first integral. Okay, this, let me just note it in the next slide. Okay, some the constant of the motion is also called a first integral. Okay, so the reason being very simple. So the reason being because del L over del phi dot is equal to constant is a first order differential equation. Okay, and it is obtained, okay, differential equation obtained using or obtained by integrating this del y del t del L over del phi dot equal to 0. This is nothing but our Lagrangian equation as we see in the earlier slide. Okay, so the name, that alternative name that people normally use, that first integral, is nothing because we have obtained the constant of the motion via integration of this expression here. Okay, that is why. So now what we see is that the generalized momentum associated with an ignorable coordinate is a constant of the motion. Okay, that is what we have illustrated for this spherical pendulum of mass m and length L. Okay, just to summarize once again, what we have to know is that whenever the Lagrangian function does not contain a particular coordinate, say qk explicitly in the expression of the Lagrangian, then the generalized momentum or canonical momentum associated with that particular coordinate is a constant of the motion, and that coordinate is referred to as cyclic coordinate. Now you see, whenever a coordinate is absent, then it is related with a constant of the motion. That constant can be say momentum, as we have seen, and that is conservation of momentum here. And what we have just described here is the momentum corresponding to rotation, and that would be angular momentum. Okay, this would be angular momentum of the system. Okay, so angular momentum of the system is conserved here. So we will see more example of this in the next part of the discussion. Okay, so we will continue the lecture with more discussion on the relation with the conservation theory. Okay, see you in the next class.